Good evening, and on behalf of the many people who've been instrumental in bringing us all together today, I should like to extend a very warm welcome to each and every one of you to CERN Alumni Second Collisions. Welcome back to CERN, albeit virtually. We're very proud to bring you all together on this specially designed platform, which we hope will remind you fondly of the days you spent at CERN and give you an idea of how the site has changed and how it will change further with the construction of our flagship exhibition and education centre, Science Gateway, in which we hope we should be able to welcome you for the third collisions in 2024. But I'm getting ahead of myself. For those who don't know me, my name is Rachel Bray, and I'm head of CERN Alumni Relations. And together with the Second Collisions Organising Committee, we'll be guiding you through this remarkable event. This weekend is about you, those of you who have contributed to this incredible, fascinating and multifaceted laboratory, CERN. Over the course of the next 3 days, we will encounter inspirational speakers, all of whom are working in highly impactful fields, changing the world for the better. All of whom were able to use their CERN experience as a foundation and are now in a position where they're changing the world. The CERN Alumni Network now has more than 7,000 members. This means more than 7,000 people who can support CERN's mission and that of fundamental research. More than 7,000 members working in diverse and impactful fields of research and industry, and more than 7,000 people to support one another with advice, mentoring, and sharing their experience to benefit others. The theme of this event is Research Matters. We all know that fundamental research impacts society in more ways than may be immediately obvious through the knowledge generated and technologies developed. But the most immediate impact is often through its people. CERN alumni are making their mark all around the world, across a wide range of fields and in diverse communities, in part thanks to the experience they developed whilst at CERN. As well as our members of the CERN Alumni Network, we're also welcoming participants from CERN's High School Teachers Programme. They're instrumental in sparking curiosity in our future scientists and engineers. We're also welcoming former students who have taken part in CERN's High School Students Internship Programme, who've acquired a taste for collaboration and research during their time at CERN. It also gives me great pleasure to welcome representatives of our member states, associate member states, non-member states, representatives of CERN experiments funding agencies who make our collaborative work at CERN possible. Now a few words about what you can expect this weekend whilst you visit the various virtual CERN locations. You can find the event agenda in the menu on the left of your screen. Talks will take place either in the main auditorium, the Globe Auditorium, or on the Esplanade des Particules opposite the Globe. Many thanks to all of our speakers and moderators for their enthusiasm and participation. Virtual visits of the experimental areas will take place on Saturday at 4:30 Central European Time. To join one of these fascinating live tours, please navigate to Building 40. Don't worry, if you miss one of the visits or one of the talks, you can return anytime you like to watch the visit or the talk from Saturday evening. We extend our thanks also to the wonderful guides from each of the experiments and the visit service who have made the visits possible. This event is also about networking and bringing you together to share ideas and experience. From the networking button in the menu, you'll see the list of participants with whom you can exchange, one-to-one at any time. We've also organised networking tables hosted by our speakers, alumni volunteers and representatives of CERN management in an Ask Me Anything. Now's your chance to start a conversation with those who have the answers to your questions. CERN alumni companies will also be presenting from networking tables at various times over the course of the weekend. You'll find several booths in Idea Square. Those include CERN activity-related booths, booths hosted by CERN alumni companies and startups, as well as recruiting companies keen to recruit from within the CERN alumni talent pool. We'd like to say a big thank you to the Lausanne-based company Evoque, our sponsor, who are currently seeking CERN alumni talent, so pay them a visit to find out more. If you have any CERN alumni-related questions or suggestions, please also visit us in our booth in Idea Square. For the first time ever this evening, we shall be celebrating alumni who have gone above and beyond to support and help develop the CERN Alumni Network, and alumni who have enjoyed remarkable career trajectories after their CERN experience. Don't miss the awards ceremony this evening at 8:15 Central European Time from the Globe Auditorium. If you have questions or issues with the platform or related to the event programme, please visit our friendly volunteers waiting to welcome you in Building 33, CERN reception. It now gives me immense pleasure to introduce you to one of the Second Collisions Committee members who will be hosting the event with me, Analia Karaginova Ferrer. She's a CMS physicist, an entrepreneur, and former deputy chairperson of the CMS Young Scientist Committee.
Thank you, Rachel. I'm very excited to be here with everyone for Second Collisions, which we have been preparing for you for the past 11 months. I'm looking forward to meeting and interacting with many of you. In the meantime, I am honored to introduce Dr. Fabiola Gianotti. Dr. Gianotti has been a research physicist at CERN since 1994. Dr. Gianotti became Director General of CERN in January 2016, and in November 2019, she was reappointed for a second term. Thank you very much for joining us, Fabiola. The floor is yours.
Thank you very much, Analia, and a very warm welcome to you all to this second Collisions event of the CERN alumni. And I would like to thank you for being with us today, and in general for staying connected with CERN. And actually, this was one of the main goals when we established the alumni network back in 2017. As of today, actually, the network counts something like 7,000 members. So thank you very much for your engagement with CERN. I would like, first of all, to thank the people who have been so instrumental in creating the network and, of course, being able to support it and to develop it. And first of all, Laura Steveni, who has been the project leader with a lot of commitment and enthusiasm until last year, and now Rachel Bray, who has taken over with similar enthusiasm and commitment at the beginning of this year. You, the alumni, the CERN alumni, have a very important role to play. Because you can be very good and credible ambassador of CERN wherever you live, wherever you work. And we need you. We need your commitment and your support for the future of the organization. And this now brings me to my very short presentation, an introduction, which has to do with CERN today and tomorrow. So what do we do at CERN today and what we want to do tomorrow? So let me first remind you of CERN's main mission. You know it very well, but just for the sake of summarizing it, you know that at CERN we do fundamental research in particle physics. Particle physics is the most fundamental of all sciences because it studies the smallest constituent of matter and the universe. At the same time, we are a driver of innovation because we need cutting-edge technologies in order to achieve our ambitious scientific goals, and these technologies are transferred to society for the benefit of everyday life. Another important pillar of our mission is training of tomorrow, scientists, engineers, technicians, physicists, and education, outreach to the general public. And last but not least, CERN is a concrete example of collaboration across borders as it attracts some 17,000 people from all over the world. More than 110 nationalities are represented. You know that CERN was founded in 1954. This was just after a big crisis, just after the World War II. And you know that the reason for founding a new lab in Europe was twofold. On one hand, to rebuild the scientific research in Europe after the war, during which several scientists had left our continent. And so you see already in the vision of the founding fathers the understanding that the economic recovery of the continent also required investment in science and fundamental research. And the second goal was to promote peaceful collaboration between countries in Europe after the disasters of the war. And so again, the awareness already at the time that science can break walls and foster peace. And if you look at the founding convention, which was signed in 1953 by 12 member states, you will see and read many modern concepts, principles and values that are as relevant today as ever. Scientific research of fundamental character with no military purpose, results and information available free of charge to everybody. This is what we call open science today. Promoting international cooperation, so science for peace, and training and education. CERN today includes 23 member states, 10 associate member states, several observers, but also we have many international cooperation agreements with several countries, including developing countries. And in this case, our role is to build capacity. So to help the scientists in these countries and their nations to reduce the gap with the countries that are in the front line of science and technology. We have an annual budget of 1.2 billion Swiss francs. I like to use more friendly units. This corresponds on average of one cappuccino per year per European citizen. And this budget is paid, the contribution comes from the member states in proportion to their net national income. One of the secrets, one of the main reasons why CERN was so successful comes actually from this budget stability over decades. CERN could benefit from this budget for many, many, many years, and this budget plus the international collaboration and cooperation have allowed to accomplish extremely ambitious and complex projects that no single country could afford alone. This budget is used to develop, operate, and upgrade the scientific and technical facilities that are used by the CERN community of scientists. And here you can see a map of this community. You see many of the scientists come from member states in dark blue, but also from non-member states like Japan, Russia, USA, China, etc. Some of them also come from countries that are not on the front line of research and technology, like Kenya, like Azerbaijan, etc., Madagascar, etc. And this, as I mentioned before, this is a way to keep also people from developing countries engaged with science and technology. And you can also notice that some of these scientists come from countries that are not the best friend of each other. So CERN is a great example of collaboration. If you look at the age distribution of the CERN scientists, you see that the peak is at 27 years. So most of our population is actually quite young. And at any given time at CERN, we have something like 3,000 PhD students, and every year we train 1,600 young people, from technician to summer student, young postdoc, etc. Not all of them remain in research because there are not enough jobs in research, or because some of them want to do something else in their life. So where do they go? 50% of the people that leave CERN go to the private sector, so some of you are working there. Some others stay in the public domain. In concerning industry, you see that people are employed in a variety of fields, from finance to computing, communication, engineering, etc. So our goal is also to train our young people for different paths and for different professional activities, not necessarily just for research. And for this reason, we have many educational activities that target young researchers, but also students in physics, engineering, computing, high school students and high school teachers, through a large number of initiatives that I don't have the time to illustrate in details, but I would like to stress that this mission of also conquering, in the good sense of the term, also Africa and students and scientists there. And before COVID, every year we had something like 150,000 visitors coming from far away, and with a large fraction of high school students. Because we had a large number of requests, you have seen in the previous slide that we could welcome and could host 150,000 visitors on guided tours, but we typically received 300,000 requests every year. We have now launched a new project called the Science Gateway. Rachel mentioned this already before. It's our new facility, actually our flagship facility for education and outreach, targeting the general public of all ages. And it will include immersive spaces, exhibition, laboratories, and also hands-on experiments for kids starting at age 5. So you can see on the top right part of the screen, you can see a top view of a drawing showing a top view of the CERN site. You can see the globe of science innovation, and within the red circle you can see the Science Gateway, which is actually a complex of buildings. And below it you can see now a real picture taken from a drone of the work site going on, because construction has started, is quite well advanced. You can see on both sides of the Route de Mérinde that brings you from Geneva to France. We are on schedule to completing construction by the end of 2022, and the total cost is 87 million. It will be entirely covered from external donation, and so far we have secured 77 million. So if you know people who are interested in donating, making gifts for educational project, please let them know that we are still looking for some contribution to complete our project. See if I can move to the next slide. Yes, here you can see also a little bit of the content of the building. Sorry, I was too fast. Let me go back. Yeah, so again, a top view of the Science Gateway, and you see how the different buildings are going to be used and what they are going to host. We will have from left to right an auditorium with 900 seats for big scientific events or public debates related to science. Then we will have a building devoted to hands-on labs so that the kids can do experiments with their little hands and understand what being a scientist means in practice. Then the first tube will be dedicated to discover CERN, the technologies we develop and the impact on society. Another tube will be dedicated to our universe, so the big questions and what we have understand so far of the universe. And last but not least, the last pavilion will host exhibition and interactive experience on the quantum world, so quantum mechanics, quantum computing, etc. Science Gateway will be a green building powered by solar panels, and we are going to plant 400 trees. So going now to the science, we know what we do at CERN. We build big accelerators, and these are usually underground structure hosted in rings. At least at CERN now we are running the Large Hadron Collider, which is installed in the 27-kilometer ring, which was previously used by LEP. So we accelerate two beams of particles, in the case of the LHC, two beams of protons, and we bring them into collision. And then in the collision, what you can imagine, although this is scientifically not rigorous, is that protons that are not elementary particles, they break into thousands of pieces, and in this way we can understand how matters work at the most elementary level, because protons are made of quarks and interacts through gluons. So we can understand how matter works and operates. At the same time, what we can do is from the energy produced in the collision, we can produce new heavy particles. So the Higgs boson was discovered at CERN in 2012. It was actually looked for, hunted at previous accelerators for many, many years, but it was only found at CERN because only the LHC could produce the Higgs boson at an abundant rate to be experimentally observed and detected. And detection is made through particle detectors. These are instruments that surround almost the full solid angle around the collision point of the two beams, and whose goal is through very advanced and complex technologies to detect every single particle, almost every single particle that is produced in the collision, and to identify this particle and measure the energy, etc. So particle detectors give us a digital picture of the collision event. Then we can interpret and understand what happened and what kind of forces and phenomena were at play. Our scientific program is based on three main pillars. This is pretty much based on the European Strategy for Particle Physics, which is a process that happens every 6-7 years, through which the European particle physics community gets together and establish the priorities for the coming years based on what we have learned in the previous 6-7 years. So the three pillars are the full exploitation of the LHC, which is our flagship project today. We are going to start the third and last run of the LHC in February next year. And then on a time scale of 2025, we will stop the LHC and install the upgrade of the LHC, which is presently under construction. It's called high-luminosity LHC. We are also preparing for the future beyond the LHC and the high-luminosity LHC through vigorous accelerator R&D. So we are pushing the technologies on a variety of domains with a broad portfolio, but we are also in particular studying the feasibility of a particular project which has been identified by the European strategy of being the most interesting from the scientific viewpoint, which is called Future Circular Collider. And I will say a few words later on. We also have a scientific diversity program complementary to what we do at the LHC, and which is based on the very powerful and versatile system of so-called injectors. So concerning the LHC, you know it's a 27-kilometer ring. You can see the track on that picture. The two beams of protons interact, collide at 4 points of the ring, where 4 big experiments have been installed. Operation started in 2010, and ALICE, ATLAS, CMS, LHCb have been taking the data since then. And 2 years after the discovery, after the operation startup, ATLAS and CMS announced the discovery of a very special new particle, the Higgs boson. So the LHC required really a jump in the concept and technologies. The backbone of the accelerator is a system of 1232 superconducting magnets, which is the single most important ingredient that allowed us to make a jump in energy compared to the previous collider, the Tevatron at Fermilab in the US. And actually the development of those superconducting magnets, which are really amazing in terms of performance, in terms of working temperature, etc., is an example of the excellent partnership between research and industry, and we'll come back to this later on. Just a few numbers: the superconducting magnets of the LHC, being superconducting, they work at low temperature. In particular, in this case, the temperature of superfluid helium, 1.9 Kelvin, 1.9 degrees from absolute zero, minus 271 degrees. But when the two beams collide, they produce the temperature that are really comparable to what the universe experienced 1 millionth of a second after the Big Bang. We are talking about 10 to the 16 Kelvin. The experiments are also truly impressive. So here you can see ATLAS, the biggest of the 4 experiments. It has the size of half the Notre Dame Cathedral in Paris. And the other experiment, CMS, has a weight which is a factor of 2, the Tour Eiffel, to stay in Paris. So you see other numbers here. I don't want to go into the details because I don't have much time, but these detectors are clearly also very complex and ambitious projects. They are essentially underground big cathedrals. The year after the discovery of the Higgs boson, the Nobel Prize in Physics was awarded to François Englert and Peter Higgs, 2 of the scientists that had developed the model and the theory that explain how the elementary particles acquire a mass. And of course, the Higgs boson and this mechanism is very important and very relevant even for our own life, because you know that atoms are made of quarks, the basic constituents of neutrons and protons, of the atomic nuclei, surrounded by a cloud of electrons. And if quarks and electrons did not have a mass, atoms will not exist as bound state. They will not stick together. And what gives them their mass is in the interaction with the Brout-Englert-Higgs field. And so the discovery of the Higgs boson actually really explains also why we are here and why atoms actually can exist. So for those of you who still are active in physics or remember what you have done at CERN when we were here maybe some time ago, I would like to show a few pictures to show how much progress has been made since the Higgs discovery. So the top left plot shows the spectrum due to the Higgs boson. These are the points that are so overlapped with the red histogram. And you saw that when we discovered the Higgs boson in July 2012, this is a plot from CMS, the signal was quite evident on the blue background, but still with large statistical fluctuation, as you can see from the error bars around the dots. And if you see now today how this signal looks in the experiments, still in CMS, you see how clear now is the red peak on top of the background due to the production of the Higgs boson. And so the large statistic, the quite ample statistic and big statistics we have today has allowed us to measure the Higgs mass with a precision of the per mil, but also to measure the way the Higgs boson interacts with the other particles. And these interactions and these couplings are known today with a precision between 10 and 30%. So there's been a lot of progress, but still the Higgs boson remains quite a mysterious particle. The experiments, the LHC experiments, have also been looking for new particles in a variety of scenarios. New particles are needed, as we will see in a few minutes, to answer to the open questions in fundamental physics today that our current theory, the standard model, is not able to address. And you can see that they've been exploring an energy scale reaching several TeV. So we are really, with LHC, we are really exploring an uncharted territory. For the time being, we have discovered nothing, no new particles, except, of course, the Higgs boson, but, of course, we will continue, in particular, with the high-luminosity LHC phase. I also mentioned that CERN is not just a Large Hadron Collider. You can see this picture that shows the ensemble, the CERN Accelerator complex, which includes linear accelerator and several rings of different size, different depth, different age. And, of course, the function of these accelerators that are upstream of the big ring of the Large Hadron Collider is to prepare the beams and to pre-accelerate them before they are injected into the Large Hadron Collider. But these beam accelerators also have their own scientific program because they serve a large number of facilities, from the antiproton decelerator, which is an antimatter facility, to Isolde, which is a radioisotope facility, and many, many others, which have a very interesting scientific program complementary to the LHC program. I will now move to discuss a little bit the status of particle physics today. With the discovery of the Higgs boson, we have completed what we call the standard model, the theory that describes the particles we have observed so far and their interaction. And this actually is the result of more than 50 years of excellent theoretical and experimental efforts. We have also tested the standard model with very high precision, with a wealth of measurements since the early 60s, and many of them actually done at CERN, at the previous collider, LEP, and now LHC, but also through a large number of fixed target experimental projects. It works extremely well, with no significant deviation observed so far from the standard model expectation. And this is very puzzling because we have experimental evidence and even the certitude that there are phenomena that the standard model is not able to describe. And so this calls for physics beyond the standard model. So here is a list of questions. Well, the Higgs boson still remains a mysterious particle. For the time being, we think, for what we see from his behavior, is fully compatible with the standard model. However, the experimental precision is not pushed enough really to exclude that the Higgs boson is really a standard particle and not doesn't belong to a more complex Higgs sector and a more complex theory. But there are other questions, like the dark universe. As you know, only 5% of the universe is made of the matter we are all made, so is known. The rest is a question mark. Dark matter is 25% of it, dark energy 70% of it. We do not understand why there are 3 families of particles. I showed them in my previous slides, with the leptons, the neutral and charged leptons, and the quarks behaving in different ways. So this is very puzzling. We don't know why there is so little antimatter in the universe. The universe is almost exclusively made of matter with very, very little antimatter, and so on and so forth. So these and other crucial questions require new physics and require future, more powerful colliders to be explored. So the next step is the upgrade of the LHC for the so-called high-luminosity LHC phase, which will allow the LHC experiments to record 10 times more data by 2038 of what they will have recorded at the end of the LHC, sometimes in 2024. So we are, at the moment, we are upgrading 1.2 kilometer of accelerator with new technologies, in particular developing new generation superconducting magnets based on a different material than the current LHC magnets. This material is called niobium-13 and will allow us to make a jump in magnetic field and therefore in the future also in energy, and to explore a new regime. And first modules have been produced, in particular in the US. You know that our project are the results of a worldwide collaboration, and our US colleagues have been able to build and to successfully test full-size modules of superconducting magnets based on niobium-13. And as I mentioned, we are now we have undertaken a feasibility study of a possible future collider to take over from the LHC. So the European strategy has identified the FCC as the most promising project. You know that there are linear colliders, circular collider, but the FCC was considered to be the most promising in terms of scientific return. You see from the sketch that is a 100-kilometer ring going under the Lake of Geneva and behind the Salève, so quite an ambitious project. It will host a first-stage machine that will be an electron-positron collider, like the current 27-kilometer ring hosted in the past first LEP, an electron-positron collider, and then this will be followed by a hadron collider with a center of mass energy of at least 100 TeV, so 7 times larger than the LHC today. Of course, it looks at the beginning like Mission Impossible. The LHC also looked like Mission Impossible, but of course, physicists, engineers, and technicians working at CERN are extremely motivated and stubborn and determined. So I'm sure that if this project goes ahead, we will be able to do it. China is considering a similar project, and so which of course testify to the interest of this kind of exploration, kind of instrument. In parallel, we are pursuing accelerator R&D for other options, because we cannot put all our eggs in one basket. So linear colliders, in particular through the CLIC projects, muon colliders, etc. So all this project would not have been possible without a strong partnership between CERN and industry, and I know that many of our alumni now are working in industry. So this slide gives you a flavor of what is CERN buying. We buy products, high-tech products from industry in many domains, from electronics to mechanics, information technology, cryogenics, vacuum, etc. We also need many services. We'll need civil engineering, because we continue to excavate new underground tunnels and caverns as our projects become more and more ambitious. And every year we spend more than 500 million Swiss francs from the CERN budget to purchase supplies and services, mainly from high-tech industry in the member states. Our technologies are available for society free of charge, and this slide summarizes some of the fields where our technologies find application. Of course, everybody knows that the World Wide Web was developed at CERN at the end of the 80s, but also you know that there are several applications in the medical field. For instance, using accelerators, accelerating protons and light ions like carbon ions to treat cancer in a way complementary to the more traditional radiation therapy, or technologies developed for CERN particle detectors finding application in medical imaging. Our dosimetry being used on the International Space Station, and also the use of CERN instrumentation to monitor the quality of the air and of the environment. CERN also has a network of business incubation centers, about 10 of them across Europe, where we make certain technologies available, in particular to young entrepreneurs that want to use those technologies for their business. And as of today, we have something like 45 startups based on CERN technologies. And before concluding, I would like to mention that CERN takes the environment and sustainability very seriously. And I would like to give you a few examples of what we are doing in this domain. So first of all, last year we have published our first public environment report. And the second one will be issued in just a few days, just now, essentially. I think it's a duty of a responsible and transparent organization to show what is the impact, their impact on the environment, and to set very ambitious goals in order to mitigate any negative impact on the environment. And this is what we are doing with our public report. For instance, we have set the ambitious objectives for the future to reduce our greenhouse gases emissions by 30% by 2024. So this is the first thing, mitigating the impact of CERN on the environment. The second step is also to minimize the use of energy and to maximize the reuse of energy. And here we have several projects, and the picture in the middle shows one of them. There is a project that's now pretty well advanced to use the heat from the LHC cooling towers from one of the LHC points to heat a nearby housing, so in total 8,000 people. And the third prong is to proactively identify and push technologies that could be helpful to society to reduce the impact of humanity on the planet. So there are, for instance, superconducting materials that are used and cables that are used to transport power and electricity for our project, in particular in the framework of the LHC upgrades. And these developments may find application in society for the transport of electricity with very limited losses. So I'm now coming to my conclusions. What is CERN today and what CERN will be tomorrow? Well, first of all, CERN is an example, a model of scientific excellence in fundamental physics and fundamental research. CERN is a driver of innovation with the development of technologies that are useful not only for our scientific program, but also with potential impact on society in various environments that are priorities for today, like health, environment, energy, etc. We are a place that trains the young generation and attracts talents from all over the world. You know very well that STEM education is very important nowadays because the number of STEM jobs grows very fast, and we need to prepare also tomorrow's workforce of STEM talents. CERN is a place that embraces and promotes inclusiveness and collaboration across borders, and has become a model for other similar facilities and endeavors. And at CERN, we promote and we embrace open science in all its facets, from open access publishing to open data, open source software and hardware development, education accessible to all, because we believe this is also a means of reducing inequities across the world. Thank you very much.
Thank you very much for that fascinating talk regarding the future of CERN. A clear message indeed, how CERN alumni can support CERN in the coming years. Now we have 10 minutes for questions from our alumni in the chat, and we can begin with the first one. Can you tell us why the creation actually of the alumni flagship was so important for you?
Yeah, so the alumni project was very important to me personally, and to, of course, to CERN more in general, for three main reasons. First of all, we wanted to keep the people who have been at CERN for a short time, for a long time, connected to the organization and keep these links with them and nurture these links, because we think that exchange in both directions will be very useful to CERN and maybe also useful to the alumni. The second reason, it's not of course less important, was to create a network of CERN ambassadors. And as I mentioned, as we look at the future, we need more powerful projects, and our scientific goals become more and more challenging. So it's very, very important also to have a network of ambassadors who can share with society in their professional environment, in their countries, the importance of fundamental research. I was saying at the end of my presentation that CERN is not just an example of scientific excellence, is also a value system. We promote values that are today more relevant as ever. So we think that the alumni can help us a lot and can also really do a lot for science in general. And last but not least, the alumni could help our young colleagues that decide to continue in the research, but also maybe to leave research and to go in another field, to find their path and to benefit from the experience of those who made the transition from particle physics, for instance, to the private sector, and what kind of advice they could receive. So these are the main reason. I was really so happy to see how this network developed, how fast it developed, and now we have more than 7,000 people, so it's really great.
Yeah, indeed. It's a big network. Okay, one more about what are your thoughts of the importance of the networking for the alumni after they have left CERN, and how can CERN actually help them build the professional network necessary for their success?
Yeah, so as I said, for me, the importance of the alumni network is in the relation that people can continue to nurture, and how they can benefit from each other, how we can benefit from the alumni, and the alumni can benefit from CERN, and the alumni can benefit from the various members of the network. It has to do with building partnership, it has to do with helping each other, it has to do with promoting values that we all cherish and we all believe in. And in particular now we are just hopefully out of a crisis, well, not yet completely out, but I hope that we now start to see the light at the end of the tunnel. And I think that this crisis, the pandemic, has shown how important science is, that we have to trust science, and actually science took us out of the crisis, how important collaboration across borders is, how important is collaboration between different disciplines, how important collaboration is between different sectors, private and public. And the CERN alumni actually reflects all these varieties, all these aspects, from geographical spread, from collaboration with private and public and different disciplines. So I think that we have to continue in this direction.
Indeed. One additional question from the chat is asking about possible collaboration with us in CERN and China regarding the development of the 100-kilometer collider.
Yes, of course, we have to collaborate. I guess that it will be very difficult to build two machines of the same kind, because these projects are not only expensive, but also require human resources, intellectual resources, accelerator, detector experts, computing, etc. So I don't see how the community could really, face and develop, build and operate two such machines. And it's not also justified from the scientific viewpoint. Of course, two complementary colliders, like a linear one and a circular one, there are elements of complementarity, but two circular colliders are exactly the same thing. So because there is no space and no room for those two machines in parallel, I think we'll have to work together. And so we will see, of course, if Europe decides that a future circular collider is what we want to do in Europe because it's the best motivated project, I think we'll have to fight in the nice sense of the word to have it here at CERN, and how to say, and try to convince our Chinese colleagues to work with us.
That's true. A few more questions are popping out, which is good. It's nice to see that the chat is active and all the alumni are actually interested in everything that is happening right now. They are interested at what are the most promising investigations that are taking place right now.
Yes, excellent question. So from the point of view, well, we are investigating different things in different domains. For instance, Science Gateway is also an investigation in the field of education and public engagement and outreach. But in the field of science, so first of all, for what concerns the research we do, so research in particle physics, the focus is to try to address and possibly answer the open questions. And I've showed a list of them. They go, first of all, for a better understanding of the Higgs boson, which is a very special particle. I didn't have the time to go into details, but you know, the Higgs boson is completely different from the other 16 elementary particles that had been discovered before. It got different features, we call them quantum numbers in physics. It brings a different type of interaction, so interacts in a different way. So it's quite unique. It has a special role. I mentioned the role of providing masses to the other elementary particles. So there is something very special with this particle, and we believe that the Higgs boson can be the key to link the standard model to physics beyond the standard model, the new physics that we are looking for and we hope to discover one day. So the Higgs boson can tell us a lot about this new physics. We hope, we think, but of course it remains to be demonstrated. So the Higgs boson is one thing, but also there are many other questions. I mentioned dark matter, which is a big question mark. So and matter-antimatter asymmetry. So CERN, with its current project, the LHC and the Scientific Diversity Project, and of course even more so with the future more powerful accelerators and colliders, will hopefully allow us to make a big step forward in our understanding of fundamental physics. From the technology viewpoint, I mentioned development, for instance, in the field of superconducting magnets, where we are now developing a new generation of high field magnets based on new materials, and we hope that these developments also will find wide application in society, but will allow us to push our energies to the next frontier. And there are many other technologies that are being developed at CERN. For instance, in the field of computing, quantum computing is, of course, a new focus nowadays, not only at CERN, but also, you know, in all countries where governments have invested quite substantial funds for quantum technologies. But these are just a few examples.
Yeah, that last part of your answer was actually very nicely leading to the next question. With the increasing beam luminosity, our alumni are interested in how CERN plans to tackle the challenges of processing much bigger data volumes.
Yes, exactly. So it's a very relevant question. I don't think quantum computers will be available already on the time scale of the high luminosity LHC, but yes, the high intensity of the beam will offer new challenges to the experiments that go in terms of amount of data, in complexity of the event themselves to be analyzed. So how to tackle this? This goes through several pronged strategy. One strategy is for the experiments and they already started and are continue to work on this, to develop data management model, way of compressing the data, fast simulation tools, faster reconstruction in order to reduce the storage that is needed in terms of petabyte, and also the number of processors, so the computing, the processing power. So they're working on, for instance, multi-thread reconstruction software, etc., that will allow to also to make the best use also of the hardware that we have today. The other direction is to exploit the fact that, of course, with time, for a given amount of money and a given cost, the processing power and increase quite substantially, 20% a year typically. So on a time scale of several years from now, say 10 years from now, of course, we will have much powerful capacity and much powerful tools for the same cost. But we are not yet there, but I think that there has been a huge progress recently where the experiments have been able to show how well how effective they can be in the usage of their resources. But we will continue, and I think we will make it.
Wonderful, thank you. And I would like to ask you a little bit more personal question, if you may. Looking at our alumni and looking at their wonderful trajectories that they have taken after leaving CERN, it makes me wonder what path you would have taken if you did not pursue a career in particle physics.
It's a very difficult question. I had several interests, you know. I loved music, but I don't think that I would have made music my profession. It's rather a hobby. So if I had not undertaken a career in particle physics, I think I would have studied neurosciences. I've always been fascinated by the brain, by complex things, and also, you know, about how things work. And the brain, for me, is really something, you know, very special and amazing and really very, very attracting. So maybe I would have become a neuroscientist. Now it's too late, unfortunately.
Another fascinating scientific field. Okay, thank you very much, Fabiola. Such an insightful talk, and thank you very much for your candid replies to our alumni questions.
Thank you very much, and have a nice meeting.